So tell me what processes you simulate.
Sure. Right now we're primarily handling laser powder bed fusion and directed energy deposition. So laser powder bed fusion would be something like an EOS or SLM process where you're actually raking across a layer of powder and you're lasing it, and then the build platform drops and you rake across a new layer of powder. A DED process is like a free form deposition where you have a robot arm and some sort of substrate to deposit on, and the substrate could be moving independently of the robot arm. Basically just like a multi-bead welding.
So what are the important considerations when simulating like DED versus LPBF?
We'll go the whole way back to that question again here for the DED. So the other big thing we're up to is making part scale DED models, and how the part scale DED models differ from legacy approaches is that there really aren't part scale legacy approaches for DED. There's a lot of powder bed tools out there, but the DED models on the market are not part scale. They're primarily moving source models. So they actually are simulating the motion of the heat source everywhere, which is extremely time intensive and has convergence issues and becomes a somewhat academic exercise. But if you want to simulate a several meter long DED component, or so we see very large like casting and forging replacement components, there's nothing at all out there on the market. So we just made a big investment in DED. So we have a release coming out next week that'll push this even further, but we have the first like truly part scale DED model. The big considerations for DED that you don't have to worry about in powder bed is that in DED, the directionality of the deposition is very important. One of the reasons that these powder bed models, one of these reasons that the legacy models work for powder bed is because you have a rotation of the scan vector between the layers, and this basically homogenizes a bunch of the mechanical response. So you don't have to be aware of what every vector is doing to get a good prediction in a powder bed simulation. That's completely different than DED. DED is more like a welding simulation where the beads typically are all going to go down in the same direction, and those beads are going to have really high stresses in the direction they're traveling, and they're going to have really low stresses in the transverse direction perpendicular to the direction they're traveling. So there always has to be this awareness of the directionality of the vectors. So our part scale tool is basically taking in the actual G code, generating a mesh of any arbitrary geometry. It doesn't have to be a 2.5 axis planar type deposition. It could be a situation where the table is turning and the robot is moving. You can generate a mesh from that, but then you can also apply the strains based on this in the part scale modeling. So it's like a truly general inherent strain model for DED. And the other benefit that you get with this approach is that it eliminates the convergence issues that people experience with moving source models, and it's extremely scalable because it rests on the same solver that we built up our powder bed technology on. And that thing was architected to handle things like meter tall rocket components or heat exchangers and things like this. While the DED components we see are very large, they aren't geometrically complex compared to a powder bed part. So we can typically get we could predict even a very, very meters long DED component with hundreds of layers or thousands. Something like that would be able to get a thermomechanical prediction in minutes on a laptop. So we see, I think we could, even if we didn't have the powder bed model, I think we could build the entire business just off of the opportunity that we see in DED and also cladding.
Why don't we move on to the types of materials that the simulation software supports, and how might a user add a new one?
So the software, as Eric was saying earlier, is extremely general, and the constitutive model that we're using is also very, very flexible. So in terms of what materials and processes are supported, it's really pretty much whatever is being printed today on modern machines is either included or could be included relatively easily. With just some basic material properties and a calibration, which is really not very onerous at all. So one of the things that we sort of had to rethink for this company was how we wanted to do that calibration, because there's kind of a wide range of ways people calibrate. So we explicitly model the thermal, and then we calibrate for the mechanical only using a set of calibration cantilevers. So what that lets us do is we do a single calibration for any temperature, which is very flexible for different process conditions or different geometries. And by isolating the mechanical only component, we can also extract different types of strain. So the in plane, the out of plane, spring back components can all be calibrated independently. So it's it's quite a bit better approach to get a more accurate result, the first time.
People don't want to put their stuff out on the cloud. People don't want expensive GPUs. And when it comes to how do we onboard the materials, what people want is they want to be able to input things they can easily determine, and they don't want an endless calibration process. One calibration that lumps in most of the unknowns in the model, so they don't have to know their yield stress at 80% of melting or their laser absorption efficiency.
That makes sense. So do you see that as something different than just say even a year or two ago? And then on the opposite end of that, do you see that changing, that like what the next trend will be of what they're demanding?
I don't know if it's been in the last year or so, but the trend is towards bigger, more complex geometries. Those are the things that have the business case to be printed in additive. So, and I think that in terms of what the market demands, it's going to be continually faster, more scalable models. So as soon as it's the nature of the end user that as soon as you address the need, they immediately take it for granted and say, it's great that PanX can run 1,000 times faster than a legacy tool for these geometries. I want to go even. They'll just expand to adopt it more and then ask for more and more and more, which is great. I mean, that's the attitude that kind of drives the innovation.
So let's see, how about considerations that might be needed when performing tight tolerance compensation as opposed to a design study?
For something like a design study, I'll start with that part of the question because it's a little bit easier, but a design study is more of a comparative study, right? Is this thing going to deflect more? Is it going to deflect less? Is this going to have more stress? Is it going to have less stress? That type of prediction is a little bit more forgiving. Usually one of the things you want out of that type of prediction is speed, right? You want to be able to maybe evaluate 20 designs very quickly. So the reason our solver is very good at those types of things is because it is so much faster than the legacy approaches, because this multi-grid approach. And for something like that, you can neglect a lot of detail. Like the main input into a design study might just be the geometry. You can turn the thermal part of the model off entirely for a lot of these types of studies. Just run it as like a mechanical analysis that would look more like a typical inherent strain tool that's a popular type of model to run for these applications. For the tight tolerance compensation, you have to include a lot more detail in the model. So what we're doing for these types of problems is we're meshing even the finest details. So it could be 150 to 200 micron thin feature that has to be resolved in the FEA mesh because it's going to need to be compensated. We need to include everything that's on the build plate. We include all of the energy input from the machine. We include all the timing from the machine. We include conductivity through the loose powder between the parts. And the reason we need all that detail is because these parts are going to get very, very hot, and the thermal strain is not going to be negligible. You can't just ignore it like in a traditional inherent strain tool. But to calculate that thermal strain that's going to impact the distortion, you have to have extremely accurate temperature prediction. So you need to lump in all that extra information in physics that you can't even input into the legacy tools. So I think that I think of the design study as kind of being the low fidelity end of the modeling spectrum, and then really a tight tolerance compensation being the extreme high fidelity end of the spectrum. And we can do both of those ends.
Yeah, so I mean, I think Eric touched on a lot of the key components. I will just touch, make a couple comments based on my own experience. So we, in my previous job, we would be interested in doing geometry compensation, for example, and you'd be looking at a component that maybe you have a bunch of them on the build plate, but it's very detailed and it's got a lot of small features. So you might make the trade-off to just simulate one maybe in the center of your build plate and just hope that the rest of them are going to behave exactly the same. And the truth is that isn't how these parts behave. If you have a single part in the middle of a build plate, it's probably going to be relatively cool, and it's going to build relatively fast because you don't have to process everything else. But as soon as you surround that with other geometries and other build coupons or things like that, the complete, environment that is now being welded in is different. So if you don't include those physics, you're going to be missing out those things. So we definitely see that as a big advantage for us, because we can simulate really whatever you have on your build plate at whatever accuracy you need to be successful for your compensation. So that's definitely a huge part. And then we also, need to be able to export, very good, high quality compensated STLs or 3MF files. We have a couple of different formats that most of our users use. And so we have tech tools around that as well. So even if you give us a relatively low resolution geometry, we can refine that before exporting it.